Hello everyone, thanks for watching our YouTube channel. And this is Juntao Yu from Cornell University, the Dali Group. And today I'm going to share with you one of our this year's ACL paper, the named entity recognition as dependency parsing. So normally the named entity recognition task can be can be classified as two different tasks. So one is called the flat NER, which only focuses on the named entities that are not nested. Take a look at this example, Microsoft founder Bill Gates. So in a flat NER setting, we will only have one named entity here, which is Microsoft founder Bill Gates. While the kernel share task 2002, 2003, and the Antu node were all annotated in this way. And normally for the flat NER, people use the sequence labeling as a sequence labeling task. So which meaning that you use BIO labels to label each individual words of the sentences, and then you create the named entities in the post-processing. Whereas another types of the NER called nested NER, which is more realistic, that also considers the nested mentions. Meaning that so in the same Microsoft founder Bill Gates cases, we will have two mentions here. Microsoft is a mention, and the Microsoft founder Bill Gates is another mention. Such a scheme has been used by the ACE 2004, 2005, and also the GINA corpus, which is a medical corpus. So people use all different ways to, trying to solve the nested NERs. Some of the examples, such as the multi-iteration sequence labeling or the sequence-to-sequence modules. For the multi-iteration sequence labeling, so you use the take the multi-iteration sequence labeling as an example. So you first do a sequence labeling on all the words in the sentence, and then after you extract some of the mentions, such as we found a mention Microsoft founder Bill Gates, and then we feed the system again those mentions, not the sentence. This time we give the mentions to the system and ask the system to label those mentions so the system can label the Microsoft as a different mentions. So in this way, it do it iteratively, and then eventually you can label all the nested mentions. In our case, we try to solve both the flat NER and the nested NER as just one simple system, which is it's an idea from the dependency parsing. So for normal dependency parsing, you were given a sentence, and the task is trying to find the head of each words, each tokens in the sentence, and also their relationships, such as the subject, object, and so on. Whereas when we cast the NER as a parsing task, we have slightly different rules. So we're not trying to find the head for each individual words, but instead we're trying to find the start indices and end indices. So which meaning that given general, we're trying to find the end of the mention, which here is the US, but we have a few differences compared with traditional dependency parsing. So first, not every start indices will have corresponding end indices. And secondly, it can be start indices corresponding to multiple end indices, such as our system were allowed the General Electric as one mention and the General Electric of the US as another mention. So this is allowed date. And secondly, so the start and end indices can be exactly same words, such as in here, the China cases, which is which is an example of this can. And also, I mean, due to the nature of the end indices, should always be equals or larger than the start indices. So the arcs were always to the left, not the bidirectional. And in terms of the network architectures of our system, we use three different word embeddings. The first is a BERT embedding, and then the faster text embeddings, which is a context independent embedding, and also the CNN-based character-based embeddings. So after we gather all those three embeddings, we concatenate them and feed it into bidirectional LSTMs, multi-layer ones. And this is our to create our initial word representation. After that, we will project those word representation into two different versions of the representation. One for the start of the mention and one for end of the mention. So that is mainly because the words that usually be the start of the mention and the words that usually be the end of the mention are quite different. So by using two different representations, it will give us a better result. So after we gather those two different versions about the word representation, we put it into a biofan classifier. A biofan classifier is initially used by the dependency parsing to create a scoring matrix between the each of the individual words. It's kind of like a matrices. So I will show this in the next slides. So right-hand side is just the parameters, detailed parameters we used in our module, and it also can be found in our paper as well. So let's take a look at the output of the biofan classifier. So the biofan classifier gives you, after you put into the start and end indices, and after some I mean the matrix multiplication, you will get those matrices. So which gives scores for each of the individual each of the individual token combinations. However, due to the nature of the end indices should be always larger or equals than the start indices, we only use half of the scores. So we discard the other half, which we marked as a dashed line here, meaning that when the end indices is smaller than the start indices. So this is against the definition of the start and end indices. And after that, we will run an argmax for all the labels, all the NER labels, and plus one more label called the non-entity. And then the argmax scores will be used as scores for this pair. And after that, we will use some simple algorithms to create our final nested mentions or the flat mentions. So let's assume we have a sentence here, and we have some candidates after removed all the candidates that had a label of non-entity. So here we have 4 different candidates: the US, General Electric of the US and the Southwest, and the Southwest Medical. So, and we've already sorted by its score from high to low and associated with it predicted classes. So for nested NER, here we will select the first mention, the second mention, and the last mention. We will not select the third mention. It's mainly because it crashes boundaries with the previous mention, and this is not allowed for the nested NER. And for the flat NER, we will have an additional rule which prevent the nestedness about the mentions. So in this case, the second mention, the General Electric of the US, will not be selected. So after we build our systems and we evaluated our system in all different settings or different corpus, So which for the nested NER, we evaluated 3 major nested NER corpus, which includes the GINA corpus, ACE 2004, and the ACE 2005 corpus. So as we can see from the table, our modules always outperform the previous state-of-the-art system that also uses the context-dependent contextual embeddings, such as BERT, Elman, and so on, by large margin, from like at least 1 point and to up to 2 points, more than 2 percentage points. And for the flight NER, we evaluated on the 5 different corpus with 2 different variants for the German corpus as being evaluated by the previous work. And for the Antu node, we have, for all the Kono share tasks, we only have 4 labels. And for the Antu node, we have like 80 different name and entity classes. Despite the Antu node is more complicated, and the previous system works well on the Kono share task data, usually worked slightly poor when evaluated on the Antu node data. However, our system seems to not affect that much by the differences. The result on the English Kono share task data and the Antu nodes are very similar in our case, but not the previous cases, such as the Chiu paper. They have a 91.6 on the Kono English data, but only has 86.3 on the Antu node. But ours, and as well as the Strubel system as well. So for the final result, our system again outperform all the previous state of the art, and with a large margin on, I mean, 4 of 5 out of 6 evaluations, and only the Kono English, because the score previous system already achieved a quite high score, and our score is just slightly better than theirs. But all the other evaluations, our system again outperform the previous state of the art by at least 1 percentage point. And for the code, so we provide all the pre-trained modules used in our evaluation, and also the code itself as well. All can be found at my GitHub page. And feel free to take a look and send us emails if you have any questions or the issues regarding our words. And thanks for listening, and hope you enjoy the video. Thank you.